Good evening, everyone. Welcome back to the Popular Science Talk session. It is my pleasure to introduce our second speaker of the session, Dr. Brishti Guha. She obtained her PhD in economics from Princeton University and is currently an associate professor at JNU. Her research areas are game theory and law and economics. She also writes in newspapers and appears on podcasts about ancient India and has a forthcoming book on the subject with Westland. The title of her talk today is Maths, Women, and Ancient India. Let us welcome Dr. Guha.
Okay, thank you everyone. I'm delighted to be here. So this is a summer school for math and it's for women. So I'm going to talk about math and women in ancient India. So I will focus on math in ancient India and I'll also talk a little bit about the role of women in learning math. Okay, so let's go all the way back to the time of the Mahabharata. So, one key episode in the Mahabharata is that the Pandavas had to go for exile for 12 years after losing their kingdom in a game of dice. And when they did that, their wife Draupadi also went with them. So Draupadi was married to all 5 of the Pandava brothers. Okay, and during that time, they were visited by Krishna. So Krishna had a wife of his named Satyabhama accompany him. So Satyabhama keeps observing the interaction between the Pandavas and Draupadi during this visit. And she is really impressed because she sees that, my God, all 5 of these brothers are completely smitten with Draupadi. They just keep staring at her face all day and they do whatever she tells them to do. And I just have one man and I still can't control him. So then she goes to Draupadi and she asks her, what's your secret? Okay, so I will read out the Sanskrit shlok in which she does that and I will tell you guys the meaning. Okay, Tava Vashyahi Satatam Pandava Priyadarshane Mukha Prekshascha Te Sarve Tattvam Etad Bravihi Me. Okay, so first she is addressing Draupadi as Priyadarshane, which means, oh beautiful one. Okay, Tava Vashyahi Satatam Pandava means the Pandavas are always under your control. Mukha Prekshascha Te Sarve, they all keep looking at your face. Tattvam Etad Bravihi Me, so tell me what's happening here. Okay, so then Draupadi says that it's not what you're thinking about. So I'm not brewing any love potions. I'm not giving them any drugs. The reason they respect me so much and why they look up to me is because I actually take care of their treasury. So I am the treasurer of the Pandavas. So then it turns out that during the whole time that the Pandavas were ruling their kingdom, they did not hire any other official to look after the treasury. Draupadi was the only one who knew the income and the expenditure of the kingdom. Okay, so she says that in this shloka, Sarvam Ragyah Samudayam Ayam Cha Vyayameva Cha Ekaham Vedmi Kalyani Pandavanam Yashasvinam. Okay, so she is addressing Satyabhama as Kalyani, which means the Blessed One. And she's telling her that I look after the king's entire ayam, income, and vyayam, expenditure. Ekaham vedmi, I am the only one who knows. Okay, so she basically knows finance and accounting, and she's keeping track of the entire accounts of the kingdom. Okay, also then she goes on to say that whenever Yudhishthir went on a trip, I would know exactly how many horses went with him, how many elephants went with him, and sometimes the king's subjects also followed him. So she kept count of all that. So in the shloka here, you actually see lots of numbers. Shatam Ashwa Sahasrani Dashana Gayotani Cha Yudhishthirasya Anu Yatram Indraprastha Nivasinaha. Okay, so Shatam is for 100, Sahasram is 1,000, Ayut is 10,000, Ashwa is horses, Naga means elephants. Okay, Indraprastha Nivasinaha, inhabitants of Indraprastha, which was the Pandavas' kingdom. So she's counting everything. So from this entire episode, okay, this episode, by the way, is from the Vana Parva of the Mahabharata. So from this episode, we can tell that at least some women in ancient India knew a lot of math. Okay, and this goes far beyond what you need for day-to-day accounting. It basically, looks at finance on a large scale, because you need to know that if you're taking care of the accounts of a kingdom. Okay, so now let's go back even further to Vedic times. Okay, so if you look, we actually look whether we can tell anything about numbers in the Rig Veda. So there is a hymn in the Rig Veda where they are mentioning numbers which are powers of 10. So they're mentioning 10, 100 and 1000. So in this sloka, which is from the Rig Veda, the first line is not important for us. If you look at the second line, you'll again see these numbers: Sahasram for 1000, Shata for 100, Dasha for 10. Okay, so what that tells us is that Rigvedic Indians were using powers of 10, so they were using a decimal system. Okay, so now let's also talk a little bit about ancient astronomy, because astronomy is very closely connected to math. So there are actually two very old astronomers called Parashar and Vriddha Garga, and actually a scholar based in Bangalore called Professor Iyengar has found the dates of these two, and he dates them to 1400 BC. So that's 3,400 years before now. Okay, and how does he find their dates? So basically, he has found the texts written by these two people, and those texts describe the positions of various objects. For example, constellations, and they also record the sequences and series of eclipses and comets which came before them. So actually, Parashar, for example, he describes a sequence of very uncommon eclipses which occurred just before his time. And Professor Iyengar uses all this to find the dates. Okay, so an interesting thing about these two people is that they already had access to 1300 years systematic observations of the night sky before their own time. So we are going back 1300 years before 1400 BC to 2700 BC. Right, so that is smack in the middle of the Indus Valley civilization period or the Saraswati Sindhu civilization. And if you think about it, observational astronomy must have informally started even earlier, because by 2700 BC, people were saying, okay, let's actually start making notes on this. So that doesn't happen in a day, right? So this actually goes very well with whatever we know about international trade in the times of the IBC, because we know that the Indus Valley civilization people were actually trading with civilizations like Mesopotamia, which is present-day Iraq, and with Oman and Bahrain as well. So we know that from archaeological evidence from those countries, as well as literary evidence on clay tablets, we know that Indians traveled all the way to Mesopotamia and established a colony there. So it was always the Indians who were like sailing the whole way to these countries. And the question is, how did they do this? Because there were no sophisticated navigational instruments at that time, right? So they didn't have compasses. In the beginning, at least, they would not have had maps. So one possibility is that because they knew astronomy, they could actually use the position of stars to guide them. So they could navigate using stars. Okay, so after the next development, after Parashar and Vriddha Garga, is a bunch of texts in mathematical astronomy called the Pancha Siddhantakas. So these are by 5 different people, and their dates fall in between Parashar and Aryabhatta. So some of them are very old, like the Vasishtha Siddhanta is dated to around 1100 BC. So what kind of maths do they have? Well, they actually try to predict eclipses. So they have sums which can allow you to predict if an eclipse will occur and the duration of that eclipse. Okay, so now whether an eclipse will occur was knowledge which was very highly prized all over the ancient world, okay, not just in India. So I'll give you an example of that. Has anybody watched this Korean historical drama called The Great Queen Seondeok? Okay, so if you haven't watched this, please watch it. So this is basically based on true incidents. Okay, so what happens is it is set in 6th century Korea, and there are two rival politicians. Both are women, and in those days, a politician's power depended actually on whether she is able to predict eclipses accurately. Okay, so the reason is that the common people thought that if someone can predict eclipses, she must be directly connected to heaven. So there's the villainess in this, and the villainess basically she pretends that I have a direct connection with heaven, and she tries to predict eclipses, and people believe her. So people are like, she's so powerful, we must support her. Okay, but her secret is she actually has a Chinese calendar, okay, a Chinese astronomical calendar, and she's using that. Now, what the heroine does, right? The heroine is the rightful heiress to the throne. So she starts using an Indian astronomer and an Indian calendar, and she one-ups her rival, and she's able to do better. So she's able to predict an eclipse better, and that's the start of her rise. The name of the drama is The Great Queen Seondeok. Yeah. So I recommend it very highly. Okay, so actually, the fact that Indian astronomers were better than Chinese astronomers was even accepted by the Chinese. So the incident that I've just told you was from the 6th century. Okay, now in 7th and 8th century China was being ruled by the Tang dynasty, and there was an Imperial Bureau of Astronomy. This bureau had 3 divisions. So just guess what the nationalities of the heads of those 3 divisions were. Yes, all 3 of them were headed by Indians. So Indians from 3 clans, Kashyap, Kumar, and Gautam. Okay, so the reason that the Chinese were bringing in Indians to head their astronomy divisions is because they actually realized that Indians are are able to make more precise calendars. Okay, so now let's come to something which all of you might be familiar with, which is the zero. Okay, India and the zero, but I'll be talking about it a little differently. So, well, some ancient civilizations just didn't have a zero. So, Egyptians, Greeks, and Romans did not. But India wasn't the only ancient civilization with a zero. So, there were Babylonians and Mayans. So, the Babylonians came up with a symbol for the zero around 300 BC, and the Mayans did so around 36 BC. But there was a big difference with the way that they treated zero, because they never really seriously treated zero as a separate number, in the sense that they did not try to find its properties or where it lies on the number line. How do you add, subtract, multiply, or divide with zero? So they didn't do any of that. Instead, what they said is that the value of the zero basically derives from the digits to the left of the zero. Okay, and this is just 3 graphical depictions of the Mayan zero. So they always had these weird faces for different numbers. Okay, now was India different? Okay, so actually the symbol for zero starts appearing pretty early in India. So it appears for the first time in a manuscript called the Bakshali manuscript, which is dated to the 2nd century BC. So I'll talk more about that later. But the person who really treated zero as a distinct numeral was Brahmagupta. So Brahmagupta worked in the 6th and 7th centuries AD, and he basically investigated the properties of zero and where it lies on the number line and how to perform arithmetical operations with zero. Okay, and he also gave a very nice definition for zero as what remains after you subtract a number from itself. So he wrote all this down in a book called the Brahmasputa Siddhanta, or the opening of the universe. He wrote it in 628 AD. And then the zero basically traveled out of India. So let's discuss how it did that. So about 100 years after Brahmagupta, a caliph named Al-Mansur was ruling in Baghdad. And then an Indian scholar named Kanka visited the caliph. And he told him about Brahmagupta's works. So the caliph said, okay, I have to get this translated. And he commissioned a man named Ibrahim Fazari to do the translation. So the translation is called the Great Sindh Hind. So as a result of the translation, the Arabs got to know about zero and they started calling it TIFR. So now about 400 years after the Arabs got to know about it, the zero also spread to Europe. Okay, how? Through conquest. Okay, so basically the Moors, who were a community of Arabs, attacked southern Europe. So they attacked Spain and Portugal, and then the zero went to Spain and Portugal. And then it spread rapidly all over Europe because European businessmen really loved the zero. Okay, so they liked it because they said that it provides a beautiful way of balancing our accounts. Okay, however, as much as merchants liked the zero, governments disliked it. Okay, so governments said, oh, we are not happy with this zero. You can just add a zero at the end of any number. In fact, you can add more than one zero. And then what do you have? You have fraud. Okay, so then some governments went as far as to ban the zero. Okay, for example, the government of Florence, which was an Italian city-state, officially banned zero in 1299. So merchants said that, well, we don't want to stop using the zero, but we just have to make it such that the government does not find out. So then they started using secret code for zero. Okay, so instead of the standard symbol, they just put in a code for zero. And if you remember, we said that the Arabic word for zero was cipher. So this became cipher in Europe. And if you think of the modern meaning of the English word cipher, it means code. Okay, so this is the reason. Okay, so another thing which Brahmagupta did was that he also gave an intuition and a conceptualization of negative numbers. Now for us today, negative numbers may not seem like a big deal, but think about ancient civilizations. Okay, now intuitively, people like to count things. Now what can you count? You can count something which is already there, but then you have positive numbers. Okay, so it's really difficult even to conceptualize zero, let alone a negative number. So Brahmagupta gave a really nice intuition by calling them renam or debts. Okay, so he said that these are like debts or liabilities of a businessman. And that's pretty easy to understand intuitively. Okay, so now I will step back a little bit from arithmetic and talk briefly about geometry. Okay, so actually, again, geometry appears way back in one of the four Vedas called the Yajur Veda. So the Yajur Veda tells people that you have to build different types of altars for different sacrifices. One altar needs to be square, one has to be circular, third one has to be semicircular, but all three have to have the same surface area. So now, because of this, it gave rise to a huge branch of knowledge called Vedic geometry. And there were these bunch of texts called the Sulba Sutras, where people were trying to work out these things. So Sulba actually means rope in Sanskrit. Now remember, people at that time did not have geometric instruments, so no compass, protractor, set square, etc. So what they did have is they had ropes. So they would usually drive a stick into the ground and tie a rope to the stick, and they would use the rope for measurements. So these books were all called Sulba Sutras. Now, the Sulba Sutra I'll talk about is called the Bodhayan Sulba Sutra. This is dated to 800 BC. It actually has a statement of what we know of as the Pythagoras theorem. The only thing is Pythagoras came 300 years after this. Okay, so obviously Pythagoras was not the first person to come up with the Pythagoras theorem. So I'm now just going to the shlokas and my translations of the shlokas where the Pythagoras theorem is mentioned in the Bodhayan Sutra. Okay, so first let's look at the English. A rope stretched across the diagonal of a rectangle makes the sum of the areas that the long side and the short side make separately. Okay, so let's understand first what we are saying. So we are saying there's a rectangle. The long side is A, the short side is B. Okay, so the long side, if we make a square using that, the area will be A square. If we make a square using the short side, the area will be B square. Now there's a rope stretched across the diagonal. So the length of that is basically the length of the diagonal. Let's call the diagonal C. Now, if that forms one side of a square, the area of that square will be C square. So this is saying that that area will be equal to the sum of the areas that the long side and the short side make separately. So C square is A square plus B square. Okay, so that is the Pythagoras theorem. So Sanskrit says, Dirgha chaturashrasyakshnaya rajju pashvamani tiryangmani cha yat prithak bhute kurutas tad ubhayam karoti. Okay, so Dirgha chatura is a rectangle, Rajju is rope, Pashvamani and Tiryangmani are long side and short side. Yat prithak bhute kurutas means make separately. Tad ubhayam karoti, add them together. Okay, now the second one is basically just a special case of the Pythagoras theorem where you have an isosceles triangle, right? So A is equal to B. Okay, the chord equal to the diagonal of a square makes twice the area. So here you basically just have a square of area A square and you have a diagonal there. So it's saying that if you make a square of which one side is the diagonal, that area will be 2A square, which means that the diagonal will be square root of 2 into A. Okay, so this is a special case of Pythagoras. And if you look at the Sanskrit, it says Sama chaturashrasyakshnaya rajjus dvistavatim bhumim karoti. So Sama chatura is square, Sama is equal, chatura is 4, all 4 sides are equal. Okay, dvistavatim bhumim karoti means makes twice the area. Okay, so now we are again coming back to arithmetic and talking about a rather important innovation in Indian math called the place value system. Okay, so the place value system, I'm sure all of you know, is just the system that when you write a number, the rightmost digit is in the units place, second rightmost is in the tens place, etc. Right, so this actually makes it very easy to add, subtract or divide because or multiply, right? So because if you have two numbers, you can just write them one under the other and then you can use the place value system. Now things were very difficult in other ancient civilizations which actually did not have this system. So day-to-day market transactions were very difficult. Okay, so let's start off by talking about the ancient Greeks. So suppose I'm an ancient Greek and I go to the market and I find I need to do a subtraction. Okay, then I'm in trouble basically. So what I do is first I draw a figure in the sand. The area of the figure has to be equal to the first number. Then I have to draw another figure in the sand whose area has to be equal to the second number. I try to subtract the second area from the first area. So first of all, you can see this is cumbersome. And by the way, this also tells us they could not deal with negative numbers because you can't draw the area of something negative. Okay, and then, things were not very easy either for the ancient Egyptians. Okay, so the Egyptian number system was such that you would need a huge number of symbols to depict a relatively small number. For example, 87 is shown with 15 symbols. Okay, 8 heels and 7 vertical lines. So this again made computation difficult, and in fact, Egyptians could not perform straight multiplications. To multiply, they just had to keep adding the same number to itself many times. Okay, now I haven't put it on the slides, but is anyone familiar with Latin numerals? No? Okay, so for Latin numerals, you basically have different symbols for the numbers, but there's absolutely no connection between the number of symbols and how big the number is. For example, 100, okay, 100 is shown just by C, okay, and a much smaller number, 18, is actually XVIII. Okay, so you're using so many symbols for a much smaller number. So, yes, Roman, yeah, so Roman is sometimes, confused with what's called Arabic as well. So I use Latin. Yeah. Okay, so again, you can see it would be really hard to add, subtract, multiply, and divide with that system of numbers. So let's talk about where positional notation appears in India. So it appears in the Bakshali manuscript that I mentioned earlier. Okay, so let's talk a bit more about the Bakshali manuscript. So first, starting with how it was found, it was actually found by accident in British India. Okay, so a farmer was digging in his field and he found something weird. So he found there's this whole collection of birch bark leaves and they're all tied together with something and they have some writing on them which he couldn't understand. So he goes to his landlord, who's an inspector, and the landlord realizes, oh, this is something important. So eventually he gives it to the Royal Asiatic Society of Bengal, where there were people who could actually examine and translate the manuscript. So then they found, wow, this is actually a maths text. Okay, so then it was later dated to between the 2nd century BC and the 2nd century AD, and currently it's kept in Oxford. Okay, also it was found in the Peshawar area, which was in undivided northwest India. Okay, so what kind of things, what kind of content did the manuscript have? So I've already said it had a symbol for the zero. It also had algebra, so it had linear and quadratic equations, and the problems were actually a lot of fun because they involved travelers' problems and animals like camels and horses. So this is actually interesting in the context of the place where it was found. Okay, so I mentioned it was found near modern day Peshawar. There was an ancient city, an equivalent of Peshawar called Pushkalavati, and this was also very near Takshashila. And some of you may know there was a big university at Takshashila. Okay, so also Takshashila and Pushkalavati were both on a major international trade route. So this was a route which ran through land. It would go all the way to China in the east. It would go to West Asia in the west. And there were constantly travelers and traders on this route. So what happened is whenever somebody stopped at a town on this route, they would want to exchange things. So for example, buy horses, okay, sell camels. And then the problems which involve travelers are also very practical. So for example, you will be given the locations of two travelers. You will be given their speeds, and then you will be asked in how many days will they meet. So this is actually very important for a trader who is expecting to meet a buyer or a supplier. Okay, and it's also a fun thing to learn for traders' kids. So you can imagine, this might be a context where traders' kids are always coming across these situations, and they're also learning algebra using those kinds of problems. And if they get really advanced, they might go on to Takshashila University instead of becoming traders. Okay, so here's a page from the Bakshali manuscript. Okay, so moving on to more developments in math. So the numbers that we use today, okay, 1 to 9 and 0, these were all actually developed in India, even though they're officially known as Arabic numerals. So the reason they're known as Arabic numerals is because the Arabs were actually the intermediary who carried these numerals to the West. So the person who's actually known for Arabic numerals is Al-Khwarizmi, but he gave credit to the Indians. So his own book is called On Calculations with Hindu Numerals. Now Hindu numerals means numerals of Hind, and Hind was the Arabs' name for India. Okay, so the ancient Indians were also good at trigonometry. So modern trigonometry started with Aryabhatta's sine and cosine tables. They were also good at algebra. So I've already mentioned Bakshali manuscript had some equations. Now Aryabhatta and his followers also did a lot of work on quadratic and indeterminate equations. And Brahmagupta and a later mathematician named Bhaskara too did pretty groundbreaking work on Pell's equation. Okay, so now, there are a few ideas in maths for which only the West is, at least most of the time, given credit, but they originated in India as well. So two examples are the Fibonacci sequence and Pascal's triangle. Okay, so the Fibonacci sequence actually appears 600 years before Fibonacci in something written by an Indian mathematician named Virahanka. But it can actually be traced back even further to a prosodist named Pingala. So Pingala is variously dated to being between 2nd century and 6th century BC. And so he's the one who came up with binary system, permutations and combinations, Pascal's triangle, and Fibonacci series. Okay, so let's talk about Pingala. So he's conservatively dated to 2nd century BC, but there are some accounts which say that he was the brother of Panini. Now Panini is dated further back to the 6th century BC. So there's a possibility that Pingala was even earlier, right? Okay, so Pingala was a prosodist. Now, what does a prosodist mean? So, prosodist is somebody who specializes in poetic meter, okay, which means the rhythm in which poetry is written. So, this was called Chanda, and the name of Pingala's book is the Chanda Shastra. So we might be surprised at first that what was a guy who knows about poetic meter, what was he doing coming up with so many mathematical concepts? Okay, so actually poets at that time were facing a problem. Okay, so the problem is like this. Suppose I have a line of poetry with a fixed number of syllables. So let's call this number n. Now there can be two different types of syllables. So there can be either long syllables, which we call guru, or there can be short syllables, which we call laghu. So the poet said, how many combinations of long and short syllables can we make if we have this fixed number of syllables n? Okay, so to solve this, Pingala came up with the concept of permutations and combinations. And then he came up with what is now known as the Pascal's triangle. In Sanskrit, it was called Meru Prastara. So Meru Prastara is just like a lookup table where you can look up different permutations and combinations. And you can also, from the diagonals of the Meru Prastara, derive the Fibonacci series. Okay, now the second thing I'm going to talk about is actually calculus. So calculus we always associate with the West, and we say that Newton and Leibniz independently came up with calculus, I believe around the mid-17th century. Okay, but somebody called Madhava back in 1300 came up with infinite series which lay the whole foundation for calculus. Okay, so who was Madhava? So Madhava was basically a mathematician who founded a school of followers, and his followers are called the Kerala School of Mathematics and Astronomy. So Madhava wrote books, then his students wrote books, their students wrote books, so on for about 300 years after Madhava. So we have access to those texts. Okay, so what kind of series did Madhava find? So one is like all kinds of infinite series, including what's known as the Taylor series. Okay, then he had a very nice expansion for pi. So pi, he approximated like this: pi by 4 is equal to 1 minus 1/3 plus 1/5 minus 1/7, etc. So it's an infinite series. You're alternately adding and subtracting. The fractions are becoming smaller and smaller. Okay, so since I've mentioned pi, you might be curious, why haven't I mentioned Aryabhatta? So of course, from very ancient times, Indians wanted to measure pi accurately. And the reason is that pi is actually what you get if you divide the circumference of a circle by its diameter. So it's 2 pi r by 2r. So it's always needed in practical terms. So even, in pre-Aryabhatta times, people were trying to estimate it. Aryabhatta improved on it, but Madhava's approximation is much more accurate than Aryabhatta's. So he also, of course, recognized, so there were no calculators at that time, right? So if you have to compute this, you have to crank it out by hand. And he actually said that at one point you will get bored. Okay, so you're just adding and subtracting and you get bored. So what should you do when you get bored? So he gave an approximation that at that point, you just stop and use an approximation for the rest of the terms in the series. So what this shows us is that Madhav understood the concept of limits. So he's actually saying that as n goes to infinity, you can use approximations for the rest of the terms. And we know limits are very important in calculus. Okay, so by the way, Madhava doesn't just give this formula. There's a proof for how he gets it. Okay, so this is a very beautiful geometric proof where he uses like arcs of circles, the concept of similar triangles, etc. Okay, so another reason why infinite series are important for calculus is that there are some functions where it's actually hard to integrate them. For example, some trigonometric functions. But if you can express that trigonometric function in terms of polynomials, then because it's easy to integrate polynomials, okay, integrating this whole function becomes feasible. Okay, so I haven't talked for a long time about the role of women. So let's come back to that with discussing a book called Leelavati. Okay, so why is the Leelavati actually important for women? Because it's probably the only maths textbook in the world where the problems are addressed to girls and young women. Okay, and this book is attributed to Bhaskara II, who was a 12th century mathematician. Now, Leelavati is the name of Bhaskara's daughter. So most of the problems in the book, they're either addressed to Leelavati or to other girls. Okay, now there is a conspiracy theory that Bhaskara wasn't the author. Actually, Leelavati herself was the author. And there are two good reasons for thinking this. Okay, first of all, Bhaskara did not just write the Leelavati, he wrote a bunch of other books. Now, in the other books, his style is very dry and formal, but in Leelavati, it's playful and it's interesting. So, the idea is probably the author of Leelavati was a different person. Okay, and secondly, we know that Leelavati actually was supporting herself by teaching math in a school. Okay, so she founded that school, she was running a math school basically. And that would also fit because if you're teaching maths to kids, then you basically get, you get a little more playful and then you put that into the problems. Okay, so let's talk a little bit about what the Leelavati contains. So the initial problems are for smaller kids, so they're very easy, they're arithmetic problems. And I'll just give you an example by reading out the translation of a problem. Dear intelligent Leelavati, whose eyes are like a fawn's, tell me the numbers resulting from 135 taken into 12, if thou be skilled in multiplication by whole or by parts, whether by subdivision of form or separation of digits. Tell me, auspicious woman, the quotient of the product divided by the same multiplier. Okay, so here you can observe a few things. First, the problem itself is simple. It's just 135 into 12. Some shortcuts are suggested for the ways in which you can solve it. But also, the psychology which is used, because this is for very young girls and they have to actually be coaxed to do the problem. Okay, most of the time they would not want to do it. So first of all, she's called very intelligent. Then she's told, you're not just intelligent, you're also very pretty because your eyes are like a fawn's. Okay. And thirdly, they actually use some psychological manipulation because they said, are you really skilled at multiplication? If you're skilled at multiplication, then solve this. Okay. So later on, the problems become harder because we proceed to algebra. Okay, and from the way the problems are set, you can also tell that the girls solving them are now older. So I'm going to the next problem, which is set in a context of romance. Okay, so again I have the Sanskrit here. Haras taras tarunya nidhuvana kalahe moktikanam vishino. The young woman's pearl necklace broke during a lover's quarrel. Okay, so hara is necklace, tara is the wire of the necklace, tarunya means young woman, nidhuvana kalahe is lover's quarrel, moktikanam is pearls, vishino means broke. So basically, she was having a quarrel with her lover and she had a pearl necklace and it broke in the process. Okay, then it says Bhumau Yatas Tribhagaha. So this means a third of the pearls fell on the floor. Shayanatala Gataha Panchamangsho Asya Drishtaha. 1/5 was seen under the bed. Praptaha Shashtaha Sukeshya. So she herself found 1/6. So actually here we are using Sukeshi to describe the girl herself, which means someone with very beautiful hair. Okay, Ganakam Dashamakaha Sangrihitaha Priyena. Her lover gathered up 1/10. Shashtam cha sutre. So 6 pearls remained on the string. Kathaya Katipaya Moktikeir Esha Haraha. Tell me how many pearls were on the necklace to start with. So here, it's a clear algebra problem. So you can use X for the total number of pearls. And then, but you can see it's an easy equation because provided you can add and subtract fractions, it's just a linear equation. So by the way, the answer is X equal to 30. Okay, then the problems in algebra themselves become a little more complicated, but the context remains interesting. So the previous one you had romance, now you have violence. Okay, so in this problem, it's set during an imaginary episode in the Kurukshetra war. Okay, so this one says, Parthaha Karnavadhaya Margana Ganam Kruddho Rane Sandadhe. Partha, enraged in battle, was carrying arrows to kill Karna. So Partha is a name for Arjun. Or Arjun is carrying arrows to kill Karna. Okay, Tasyadhena Nivarya. He let loose half of them to block assaults from Karna. Tat Sharaganam Muleish Chaturbhir Hyan. Okay, with 4 times the square root of the arrows, he killed Karna's horses. So here, Mulai is square root, Chaturbhir is 4 times, and Hyan is horses. Okay, Shalyam Shadbhir. So he used 6 arrows to kill Shalya. Shalya was the charioteer of Karna. Atheshubhi Stribhirapi Chatram Dhwajam Karmukam. He used 3 more to destroy Karna's umbrella, flag, and bow. Okay. Chichedasya Shiraha Sharena. So he used 1 arrow to cut off Karna's head. Katite Yan Arjunaha Saddadhe. So how many arrows was Arjun carrying? So again, you can use X, but here it's not a linear equation. You can already see there's going to be a square root term. So it's more complicated. Now, I solved it the hard way, and then I found that in the book itself, they've suggested these shortcuts, and the shortcuts also work. But I was envious because I was never taught these shortcuts in school. Okay, so all right, so later the Leelavati goes to more complex things like geometric progression, solid geometry, and trigonometry. Now, the Leelavati actually remained the primary math textbook in Indian schools for the next 700 years. Okay, so all the way until supplanted the indigenous system of education. Okay, so since we've said that the Leelavati goes all the way to the 19th century, let's talk a little bit about the position of women mathematicians in the West around that time. So I'm just going to talk about 2 of them. So one is Sofia Kovalevskaya. So she was a Russian mathematician and she was born in 1850. Now, Sophia's dearest wish is that she wanted to attend math conferences. Okay, so she wanted to go and listen to papers and be allowed to present her own work. Okay, but the problem is that Sophia was not married, so she could not do this because it was not acceptable for an unmarried woman to travel anywhere alone. So, what does Sophia do? Well, she gets into a marriage of convenience. And she says, this is just a marriage on paper, and it's just so that I can attend conferences. And that works out for her husband because he's actually gay and he's trying to conceal that fact. Okay, so you can find details on this story in this book called Fermat's Last Theorem. So that has a lot of, stories about mathematicians. Okay, so now I'll talk about another woman named Émilie du Châtelet. So Émilie was an 18th century mathematician, French mathematician, and she actually was working on Newton's gravitational laws. So she found out that light does not have mass. So she was, I think, the first person to find that. Now, of course, Émilie never had a formal degree in math. She was also known for being the lover of Voltaire. Now, if some of you might have heard of Voltaire, he was a key figure in the Enlightenment in the 18th century. So he was a top intellectual, a very famous writer, right? And he only became interested in science because of Émilie. So what he said is that, okay, I'll write a book in science. Now the problem is Voltaire did not know math, he did not know science. So he told Émilie, why don't you just supply all the equations and write down the theories, write down the experiments which you have done, and then I will publish it under my own name. Okay, so that's what happened. Okay, so since we are talking about the Leelavati, this is actually a page from a manuscript. So this whole thing has the problem, and this is the illustration of the problem. Okay, so the problem says there is a hole at the foot of a pillar 9 hastas high and a pet peacock standing on top of it. Seeing a snake returning to the hole at a distance from the pillar equal to 3 times its height, the peacock descends upon it slantwise. Say quickly, at how many hastas from the hole does the meeting of their two paths occur? And it's assumed that the speed of both are equal. Okay, so this is, basically you get a quadratic equation and you have to appeal to Pythagoras' theorem to solve this. Okay, so I will end by showing you how multifaceted ancient Indian mathematicians were. By that I mean that they were not just interested in math. Okay, so some of you may know that chess also originated in India. And in fact, in the excavation of Lothal, which is an IVC site, it's near Ahmedabad, they found a chessboard, and the chessboard has been dated to 3000 BC. So it's like 5000 years old. Okay, and now there is a piece in chess called the knight, and the knight needs to move in an L-shaped pattern. So for those who don't know chess, okay, I'll just explain quickly. So L-shaped pattern means that the knight can move two squares either top, down, left or right, and then one square in an immediately perpendicular direction. Okay, otherwise one square in any of those four directions and two squares in an immediately perpendicular direction. So then people came up with this maths problem called the Knight's Tour. And the Knight's Tour said that, well, you can start from a square on the chessboard, and given that the knight has to move in this L-shaped pattern, is there a way in which he can visit every square on that chessboard without visiting any square more than once? Okay, so this is actually in the class of Hamiltonian graph problems, and it was solved by Euler in the 18th century. But it had actually been solved 900 years before that by a literary critic, a Sanskrit literary critic named Rudrata, in a book called the Kavyalankara. So what he does there is that first of all, he gives a solution for the Knight's Tour, but then he combines it with Sanskrit poetry. Okay, so how does he do that? So he basically writes down a poem, and every syllable of that poem is on a different square of the chessboard. And there are two ways of reading the poem. Okay, you will get the same poem whichever way you read it. The first way is the traditional way, left to right, top to bottom. Okay, and the second way is in the sequence of the Knight's Tour. So you start with the same first syllable, then you go to the square in the Knight's Tour, you look at the syllable there, then you go to the third square in the Knight's Tour, okay, and so on. So the idea was that even if you did this, you would get back the same poem. Now this is only possible if you're repeating certain syllables quite a lot in the poem. But remember, it has to be done very skillfully because you must still get a meaningful poem, right? It can't just be nonsense syllables. So he was able to do all these things. So not just good at math, also good at poetry, also good at chess. Okay, so I'll end with this.
Thank you. Thank you, Dr. Guha, for this wonderful talk. We will now take some questions. Do we have questions?
Scientific discovery doesn't happen in isolation. So are there records at these times where what happened in other parts of society along with discovery?
Okay, so you are basically asking, what were the interactions between different societies?
So,
Okay.
Let's say you say that Pythagoras discovered India at some point.
Right.
Somebody use it. What happened? The other
After Pythagoras discovered it.
No, not.
Oh.
After Pythagoras discovered, we have a
Yeah.
document that says how to use it.
Yeah.
But at that time, let's say the hierarchy.
Yeah. So people were using it to construct altars and other, architectural things. So those types of records are there. Yes. Questions?
If not, then let's thank the speaker again.